Somewhere in this solar system, there is a moon with a thicker atmosphere than Earth, seas of liquid on its surface, and a chemical signature scientists cannot explain, one that looks almost exactly like the fingerprint of life. It's called Titan, and while we pour hundreds of billions into getting to Mars, we're almost completely ignoring it. But that needs to change. And here is a question. If you could invent one technology to make Mars survivable, what would it be? Let me know in the comments. I will pin the most creative answer. Now let's begin. To understand why Titan deserves so much more of our attention, you first have to understand the story we've been telling ourselves about Mars. And it is a compelling story. It really is. Mars is close. At its nearest approach, only about 54 million kilometers from Earth. It has solid ground you can stand on. Its day is almost exactly as long as ours, 24.5 hours. It has seasons, it has polar ice caps, and there is strong, well-documented evidence that billions of years ago, liquid water once flowed freely across its surface. Rivers, lakes, maybe even an ancient ocean covering part of its northern hemisphere. So the dream makes sense, right? Mars was once warmer, once wetter, once maybe even alive. It sits just next door, relatively speaking. And if we ever need a place to expand, a second world to call home, Mars is right there on the shelf, practically waiting. The problem is, that story glosses over what Mars actually is today. And today, Mars is not that warm, inviting place. It's a radiation-soaked desert with a sky so thin it barely counts as an atmosphere. The atmospheric pressure on the Martian surface is less than 1% of what you'd experience standing at sea level on Earth. To put that in perspective, imagine climbing to the very top of Mount Everest and finding the air there roughly 3 times too thick. That's still not thin enough to match Mars. Stepping outside without a fully pressurized suit would mean almost instant death. Your blood gases would expand, your lungs would fail, and the low-pressure environment would make survival impossible within moments. And then there's the radiation. Without a significant magnetic field and without a thick atmosphere to absorb it, Mars is constantly bombarded by solar energetic particles every time the sun has an outburst, and by galactic cosmic rays that stream in from across the universe. Long-term exposure to that level of radiation dramatically increases the risk of cancer and degrades the human body in ways we're only beginning to fully understand. Any crew spending significant time on Mars would need to live underground or behind serious shielding just to stay healthy. The soil is another problem. Martian dirt contains a family of chemicals called perchlorates. They're present across most of the planet's surface. In the quantities found on Mars, they are toxic to humans and disruptive to thyroid function. Growing food there is not just an engineering challenge. It carries real biological risk that hasn't been fully solved. On top of all that, global dust storms can sweep across the entire planet for months, blanketing everything in a thick haze that cuts solar power generation and makes already dangerous conditions even harder to manage. None of this means Mars is off the table. Brilliant engineers and visionaries are working on every one of these problems, but it does mean that the friendly, almost Earth-like image of Mars that lives in popular culture is doing a lot of work to hide how genuinely brutal that world is. And perhaps more importantly, it means the conversation about where we should really be pointing our ambitions deserves to be broader than it currently is, because while the world has been watching Mars, a moon in the outer reaches of the solar system has been quietly, steadily building one of the most extraordinary scientific cases ever assembled for a destination beyond Earth. A moon so unusual, so layered with complexity, so rich in chemistry and atmosphere and mystery, that researchers who've spent their whole lives studying it will tell you, without hesitation, that it stands alone. There is nothing else like it. Titan, Saturn's largest satellite, discovered on March 25, 1655, by a Dutch astronomer named Christian Huygens, who spotted it through his telescope and recorded it in his notes. Named for the mythological Titans, the primordial giants of ancient Greek cosmology. For a long time studied from a distance, covered by an impenetrable haze that defeated even our most powerful ground-based instruments. A world that refused to reveal itself until we went there in the summer of 2004, a spacecraft called Cassini, a joint mission between NASA, the European Space Agency, and the Italian Space Agency, arrived at Saturn and slipped into orbit around the ringed giant. It had been traveling for nearly 7 years. Tucked into its structure was a small probe built by the European Space Agency, named Huygens, after the man who discovered Titan 349 years earlier. And on January 14, 2005, Huygens separated from Cassini, fell into Titan's amber atmosphere, deployed its parachutes, and drifted down through that alien sky for 2.5 hours, beaming data back to Earth the entire time. When the images arrived, planetary scientists stared at their screens in disbelief. They saw a surface shaped by flowing liquid, channels, drainage networks, rounded pebbles of water ice, scattered across what looked like a dried-up riverbed or a coastal shoreline. They detected methane evaporating from the landing site, and they understood something that changed everything. This moon has a cycle. Rain falls from the clouds, rivers carve the land, lakes and seas fill up. Liquid evaporates back into the sky, a complete, functioning hydrological cycle, just like Earth's. Except the liquid isn't water, it's methane. That one revelation cracked open the scientific imagination in a way that hasn't fully closed since. Because if the processes that shape a world, the cycles, the chemistry, the constant exchange between surface and atmosphere, can run on something completely different from water, then maybe those processes are not unique to Earth. Maybe they're written into the laws of physics and chemistry themselves. Maybe wherever conditions allow, something like life finds a way to get started. And here's the thing that should keep you up at night. Titan has far more going on beneath the surface than just methane rain. What scientists have discovered in the years since Huygens landed, and especially in the last year, suggests that Titan isn't just alien. It's alive with possibilities we're only beginning to understand. Stay with me, because now we're going to get into exactly what kind of world Titan actually is, its size, its atmosphere, its relationship with Saturn, and why one single feature of that moon is enough to completely change the math on human survival in space. What you're about to hear is something most people have never considered, and once you do, you'll understand why researchers are calling Titan the most important destination in the solar system. Let's talk about what Titan actually is. Not the myth, not the name, the real thing. The physical, measurable, scientifically documented world that sits out there right now, orbiting Saturn once every 15.5 days, locked in a gravitational embrace with a planet so beautiful that astronomers who see it through a telescope for the first time sometimes go completely silent. Titan is big, not moon big in the way you might be imagining. It is genuinely, significantly large. Its diameter stretches to about 5,150 kilometers, making it larger than the planet Mercury. Let that land for a second. There is a moon in our solar system that is bigger than a planet. If Titan were orbiting the Sun directly instead of Saturn, we would call it a planet without a second thought. It has the mass, it has the complexity, and as you're about to find out, it has the atmosphere to earn that title 10 times over. And that atmosphere, that thick, hazy, nitrogen-rich blanket that wraps around Titan like a second skin, is one of the most extraordinary things in the entire solar system. To understand just how extraordinary, you need to compare it to something familiar. On Earth, the atmospheric pressure at sea level is what scientists call 1 bar. It's the pressure your body is calibrated to live in, the pressure that keeps your lungs working and your blood from boiling. On Mars, as we already covered, the atmospheric pressure is roughly 0.006 bars, less than 1% of Earth's. Barely anything at all. On Titan, the atmospheric pressure at the surface is 1.45 bars, not just similar to Earth's, actually higher than Earth's. You would not need a pressurized suit to survive on Titan's surface in terms of pressure alone. The crushing, life-ending atmospheric deficiency that makes Mars so hostile simply does not exist there. You'd need to stay warm. Temperatures on the surface hover around -179 degrees Celsius, and you'd need a supply of breathable oxygen because Titan's atmosphere is composed almost entirely of nitrogen, with methane and traces of other organic molecules mixed in. But the mechanical pressure of that sky? It would not kill you. In fact, in the right suit with the right thermal protection, you could walk outside and look up at that amber haze and breathe in the weight of a world that actually wants to hold you down instead of letting you float away. That distinction is enormous, and it doesn't get nearly enough attention in the popular conversation about space exploration. Atmospheric pressure is not just about comfort, it's about survival infrastructure. Everything about building a long-term presence on a world depends on what the atmosphere can and cannot do for you. On Mars, the atmosphere is so thin that it provides almost no protection from radiation, almost no thermal buffering, and almost no structural support for engineering. On Titan, that thick nitrogen atmosphere does all three. It shields the surface from a significant portion of the high-energy radiation raining down from space. It moderates temperature swings, and it creates a physical environment that is, in purely mechanical terms, far more similar to the one your body evolved in. Now, here's something that very few people know, and it's one of those facts that makes you stop and rethink everything. Because of Titan's thick atmosphere and its lower gravitational pull, Titan's gravity is about 1/7 that of Earth, similar to the Moon's. If you strapped a pair of wings to your arms, wide enough and shaped correctly, you could actually fly under your own muscle power, not metaphorically. Not with a jetpack, with your own body. The atmospheric density is high enough and the gravity is low enough that the physics of human-powered flight actually work. Titan is the only place in the known universe, other than certain hypothetical engineered environments, where that is true. That single fact has inspired serious engineering conversations about exploration strategies that sound like something out of a dream. Humans gliding between landing sites, mapping terrain from the air with nothing but muscle and wings. But we're not sending humans there first. We're sending something smarter. If you've made it this far into the video, you're exactly the kind who wants to look past the headlines and understand what's actually happening at the frontier of human knowledge. If that's you, please take 5 seconds right now and hit the subscribe button and give this video a like. It makes an enormous difference for this channel, NASA's Dragonfly mission. This is real. This is funded. This is happening. Dragonfly is a rotorcraft lander, essentially a drone the size of a small car, equipped with 8 rotors, a full suite of scientific instruments, a nuclear power source, and the ability to take off, fly through Titan's atmosphere, land somewhere new, and do it again, over and over. During its planned mission, Dragonfly is expected to travel a total distance of more than 175 kilometers across Titan's surface. That would make it the farthest any planetary science mission has ever traveled from its landing point. It would visit dozens of different geological sites, analyze the chemistry of the surface and atmosphere at each one, and send back data that scientists expect will reshape our understanding of prebiotic chemistry, the chemistry that leads to life, in profound ways. The mission is currently scheduled to launch in 2028. though that timeline has shifted through budget negotiations over the past several years. Arrival at Titan would come roughly 7 years later, and when Dragonfly touches down on that orange world, it will begin answering questions that humanity has been sitting with since we first realized that carbon chemistry might be universal. Here's why those questions matter so much. Life on Earth is built on carbon. Every cell, every protein, every strand of DNA in your body is a carbon-based structure. Carbon is extraordinary. It forms more different types of molecules than any other element in the periodic table by a wide margin. It connects with itself and with other elements in chains, rings and lattices of almost unlimited complexity, and it does this readily, spontaneously, under the right conditions. Titan's surface and atmosphere are saturated with carbon chemistry. The haze that gives the sky its orange color is made of a complex mixture of organic molecules called tholins, compounds formed when nitrogen and methane react under the influence of solar radiation and energetic particles from Saturn's magnetosphere. These tholins rain down onto the surface over geological timescales, building up thick layers of complex organic material that blankets the dunes, coats the plains, and collects along the shores of methane lakes and seas. Some researchers estimate that the organic material on Titan's surface is several times the total amount of all fossil fuel reserves on Earth. Not a little, several times more. An ocean of prebiotic chemistry just sitting there. Tholins have been studied in laboratories on Earth, and what scientists have found is striking. When tholins are exposed to liquid water, even briefly, even in small amounts, they spontaneously begin to produce amino acids, the building blocks of proteins, the building blocks of life. Not life itself, but the chemical precursors that, given enough time and the right conditions, might give rise to it. And this is where Titan starts to become not just interesting, but genuinely staggering. Because Titan doesn't just have tholins, Titan doesn't just have methane lakes. As we'll cover in a later part of this video, Titan also has liquid water, not on the surface, but locked away beneath it, in a subsurface ocean that scientists now believe spans the entire globe. A liquid water ocean wrapped around a rocky core, sitting underneath kilometers of ice, heated from within and exchanging material with the surface above it. Two separate chemical environments stacked on top of each other, each one potentially capable of harboring life in its own completely different way. No other world in the solar system offers that. Mars has evidence of ancient water, past tense, long gone. Europa and Enceladus have subsurface oceans but lack the rich surface chemistry. Titan has both layered together, each one buzzing with the kind of molecular complexity that makes astrobiologists barely able to sit still when they talk about it. But here's what really deserves your attention. And this was only announced in late 2025, just months before the conference in Boulder that I mentioned at the start of this video. New analysis of data from the Cassini mission, data that researchers have been carefully processing and reanalyzing for years, revealed something that shifted the scientific community's understanding of Titan's interior. There is evidence, real, peer-reviewed, published evidence, that the subsurface ocean on Titan is not just present. It may be in contact with the rocky seafloor beneath it, which means it is not a sealed frozen lake sitting between two layers of ice. It is a liquid water environment sitting directly on rock, with heat flowing into it, with minerals dissolving into it, with chemical gradients forming at the water-rock interface. On Earth, the deep-sea hydrothermal vents at the bottom of the ocean, where superheated water shoots up through cracks in the seafloor and mixes with the cold water above, are some of the most biologically productive environments on the planet. Life thrives there in complete darkness, entirely independent of sunlight, powered by the chemical energy of the rocks themselves. If Titan's subsurface ocean is sitting on rock, generating similar chemical gradients, it may be one of the most promising places in the entire solar system to look for extraterrestrial life. Not life like us, not life that breathes oxygen and reaches for the stars, but life in the deep, ancient, chemical sense, microbial, stubborn, quietly alive in the dark beneath 1 billion tons of ice on a moon orbiting a ringed giant 1.5 billion kilometers from the sun. That's the thing about the universe. It doesn't care about your assumptions. It keeps arranging itself into configurations you never expected, in places you never thought to look, in forms you never imagined were possible. Every time we've looked somewhere new with genuine curiosity and genuine instruments, the universe has answered back with something that didn't fit in the box we built for it. Titan is that answer. Writ large and painted amber, let's talk about the molecule nobody can explain. In 2010, a pair of papers published by researchers analyzing data from the Cassini mission quietly dropped into the scientific literature and caused a ripple that has never fully settled. The first paper, led by Darrell Strobel of Johns Hopkins University, found something unexpected in the models of hydrogen flow in Titan's atmosphere. Hydrogen gas flows down toward Titan's surface from the upper atmosphere. That much was expected. What was not expected was what happened next. Near the surface, that hydrogen seemed to simply disappear. Not drift away, not react with something obvious, disappear. As if something at or near the surface was consuming it. The second paper, led by Roger Clark of the United States Geological Survey, found that the surface of Titan was depleted in acetylene. Acetylene is an organic compound, a simple hydrocarbon that should be produced abundantly in Titan's atmosphere through the interaction of sunlight and methane. It should rain down onto the surface over time and accumulate, but the surface concentrations were far lower than the models predicted. Again, as if something was consuming it now. Before you let your imagination run completely wild, let's be precise about what scientists actually said, because this is a case where the careful language of science matters enormously. Chris McKay, a planetary scientist at NASA Ames Research Center, noted at the time that these findings were consistent with, not proof of, consistent with, a very specific hypothesis. The hypothesis was this: if a form of life existed on Titan's surface, breathing hydrogen instead of oxygen and consuming acetylene as a source of energy the way we consume sugars, the chemical signatures left behind would look exactly like what Cassini observed: the vanishing hydrogen, the depleted acetylene. Both of them, together, matching a predicted metabolic fingerprint. McKay was careful. Everyone involved was careful. There are non-biological explanations. Certain mineral catalysts could theoretically produce similar effects, though none have been confirmed at Titan's surface. The data is consistent with life, but it does not prove life. Science doesn't work that way, and the researchers knew it. But the fact that the fingerprint matched so precisely, that two independent observations both aligned with this single hypothesis, was enough to keep the question alive, enough to make it worth going back, enough to make Dragonfly's chemistry instruments one of the most anticipated scientific tools ever sent beyond Earth. Because here's the deeper point. When you're looking for life somewhere you've never been, you don't start by assuming it will look like us. You start by asking what chemistry is possible, what energy sources are available, and what metabolic strategies might work under local conditions. On Earth, life found a way to power itself using sunlight, using chemical gradients in deep-sea vents, using sulfur, using iron, using methane, dozens of different strategies across billions of years of evolution. Life on Earth is not one thing. It is an explosion of strategies, all sharing a common ancestor but branching outward into every available niche. Titan has niches we have never even attempted to imagine filling. The methane seas, named Ligeia Mare, Kraken Mare and Punga Mare in the northern hemisphere, are not small ponds. Krakenmar, the largest, covers an area comparable to the Caspian Sea on Earth. These are genuine bodies of liquid, kilometers deep in places, filled with dissolved nitrogen and ethane and propane alongside the methane, sitting at temperatures cold enough to make Antarctica feel welcoming. Nothing from Earth could survive there directly, but that is exactly the wrong frame. The question is not whether Earth life could survive there. The question is whether Titan life, life that evolved there, that is built from the chemistry available there, that uses liquid methane the way we use liquid water, could exist there. And the honest answer, the scientifically rigorous answer, is that we do not yet know. We have not ruled it out. In fact, the thermodynamic analysis of whether life based on acetylene metabolism in liquid methane is chemically feasible, that analysis suggests it is. Barely, marginally. But within the laws of physics, that barely, that marginally, is enough to send a flying robot across the solar system to go check. But let's pull back for a moment, because the life question, as thrilling as it is actually only one reason Titan is extraordinary, and focusing entirely on whether something is alive there risks missing the bigger picture. So let me reframe this for you. Titan is not just interesting because it might harbor life. Titan is interesting because it is a laboratory, the largest, most complex, most chemically rich natural laboratory in the accessible solar system. And what it is running experiments on, the experiments that have been running continuously for 4.5 billion years, are the same experiments that produced you. Here's what I mean. About 4.5 billion years ago, the early Earth was a very different place. The atmosphere was nothing like today's. It was rich in nitrogen, methane, ammonia, water vapor, and hydrogen. There was no free oxygen. The sun was younger and dimmer, but the surface was warm, heated partly by the decay of radioactive elements and partly by the constant bombardment of asteroids and comets still sweeping through the inner solar system in what geologists call the late heavy bombardment. The oceans were shallow and warm in places. Lightning crackled constantly through the thick air. Ultraviolet radiation, unfiltered by any ozone layer, bombarded the surface without mercy. In 1952, a graduate student named Stanley Miller, working under Harold Urey at the University of Chicago, built a glass apparatus that tried to recreate those early Earth conditions. He sealed water, methane, ammonia, and hydrogen together, applied electrical sparks to simulate lightning, and let the experiment run for a week. When he analyzed the results, he found amino acids, organic compounds, the building blocks of proteins spontaneously assembled from simple gases and energy. The experiment, now called the Miller-Urey experiment, is one of the most famous in the history of science. It suggested, powerfully, that the chemistry of life is not miraculous. It is inevitable, given the right ingredients and the right energy. Now here is the connection that should make you sit up straighter. Titan's atmosphere today is one of the closest analogues to early Earth's atmosphere that exists anywhere in the solar system. Nitrogen-dominated, methane-rich, complex organic chemistry constantly being generated at altitude by energetic radiation raining down onto a surface, accumulating, reacting. Titan is essentially running a version of the Miller-Urey experiment at planetary scale continuously across geological time. And it has been doing so for billions of years longer than our laboratory apparatus ran for a single week. When Dragonfly lands on Titan and scoops up surface material and runs it through its mass spectrometer, it is going to be reading the results of the longest chemistry experiment in the history of this solar system. Whatever it finds, whether it's amino acids, whether it's something stranger, whether it's something we don't even have a name for yet, will be a direct window into the processes that ultimately gave rise to every living thing on Earth, including you, including the neurons firing right now as you watch this video and wonder whether any of this is real. And now, I want to zoom out even further, because this is where the big picture thinking comes in. This is where Titan stops being a single destination and becomes a statement about what kind of universe we actually live in. For most of human history, we assumed that life, if it existed anywhere, would need conditions similar to our own: liquid water, moderate temperatures, a sun-like star, a rocky planet at just the right distance. That assumption was not unreasonable. It was all we had to go on. It was the only data point in our sample, but in the last few decades that assumption has been dismantled piece by piece by the discoveries of real science. We found life in the boiling water of Yellowstone's hot springs. We found it in solid rock, kilometers underground, feeding on hydrogen produced by radioactive decay. We found it in the hypersaline waters of the Dead Sea. We found it in the frozen lakes of Antarctica, locked under meters of ice, surviving on almost nothing. We found organisms, called tardigrades, that can survive the vacuum of space, survive doses of radiation that would kill anything else on Earth, survive temperatures close to absolute zero, and temperatures close to boiling water. Life on Earth is not fragile, it is relentless. It finds a way into every crack in the universe that has an energy gradient and a set of chemistry tools to work with. That revelation changed the way scientists think about life elsewhere. If life on Earth is this adaptable, if it can colonize environments this extreme, then the universe is not mostly empty. The universe is mostly waiting for the right chemistry to click, waiting for someone to look, and Titan is waiting for us to look. There's one more thing I want to introduce before we get into the details of Titan's interior ocean in the next part, something that connects the surface chemistry to the deep interior in a way that has only recently come into focus. The surface of Titan is not static. It is not a dead frozen landscape sitting unchanged since the solar system formed. It is active, it breathes, it cycles material between its atmosphere, its surface, and, researchers now believe, its interior cryovolcanism, volcanic activity but cold. Instead of molten rock erupting from the depths, cryovolcanoes erupt with mixtures of water, ammonia, and methane from the subsurface ocean below. The evidence for cryovolcanic features on Titan has been debated for years, but several candidate structures identified in Cassini radar data, including a feature called Sotra Patera and its surrounding terrain, show characteristics consistent with volcanic origin. If those features are real, if cryovolcanism is actively occurring on Titan, then material from the liquid water interior is being brought up to the surface, and material from the organic-rich surface may be cycling back down into the ocean below. Think about what that means. You would have a pipeline, a chemical conveyor belt moving complex organic molecules down into liquid water, mixing them with minerals and heat at a rocky sea floor, and cycling the products back up to the surface over geological time. Every ingredient, every energy source, every chemical gradient that we associate with the origin of life on Earth, running simultaneously on a global scale, on a moon of Saturn. The universe, it turns out, does not build one kind of world. It builds variations on a theme, scattered across billions of star systems, each one running slightly different experiments on the same fundamental question. Under what conditions does chemistry become biology? Titan might be one of the most beautiful, most complex, most productive experiments in the whole solar system, and we have barely begun to read the results. Let's go inside, not metaphorically, not speculatively. Let's talk about what the science actually tells us is happening beneath Titan's frozen surface, because the story underground is in many ways even more remarkable than everything happening above it. And it starts with a question that took decades to answer definitively, a question that sounds almost too simple when you first hear it. Does Titan have an ocean? For a long time, scientists suspected the answer was yes. The theoretical models suggested it. The math pointed toward it. If you took what we knew about Titan's composition, its size, its internal heat, and the behavior of water and ammonia under high pressure at low temperatures, the models kept producing the same result: a global layer of liquid water mixed with ammonia sitting somewhere between 40 and 100 kilometers beneath the icy surface. But suspicion is not confirmation. In science, you need evidence you can measure. The confirmation came from Cassini, and it came in a way that was almost elegant in its simplicity. Tides, gravitational tides. Saturn is massive, more than 95 times the mass of Earth, and its gravitational pull on Titan is significant. As Titan moves through its slightly elliptical orbit, Saturn's gravity squeezes and stretches it, creating tidal deformations in its shape. The amount of deformation depends on what's inside. A completely solid, rocky body deforms a little. A body with a liquid layer inside deforms much more, because liquid flows and redistributes in response to the tidal force in a way that solid rock cannot. In 2012, scientists published measurements of Titan's tidal deformation using years of precise Cassini tracking data. The result was definitive. Titan deforms under Saturn's tidal influence about 10 times more than it would if it were completely solid. 10 times. The only explanation that fits is a global subsurface ocean of liquid, most likely water mixed with ammonia, sitting beneath the ice shell. The ocean is not a hypothesis anymore. It is a measured, confirmed feature of Titan's interior. A real thing, a real ocean, global in extent, hidden beneath a shell of ice and the most chemically complex surface in the solar system. And then came 2025. The new analysis I mentioned earlier, the one that shifted the scientific community's understanding, came from a team that spent years reprocessing Cassini's radar and gravitational data with more sophisticated models than were available when the mission was still active. What they found added a crucial detail to the picture. The subsurface ocean is not sitting between two insulating layers of ice. At least in some regions, the ocean appears to be in direct contact with the rocky mantle beneath it, the ice layer above, liquid water in the middle, rock below. If you understand why that matters, the implications are immediate. If you don't, let me take you somewhere on Earth, first deep in the Pacific Ocean, along the mid-ocean ridge systems that snake across the seafloor like the seams of a baseball. There are places where tectonic plates are slowly pulling apart. As they separate, seawater seeps down through the cracks in the ocean floor, gets superheated by the magma below, and shoots back up through chimney-like structures called hydrothermal vents. The water that emerges from these vents can reach temperatures of over 400 degrees Celsius. It is black with dissolved minerals, iron, sulfur, manganese, zinc, copper, ripped from the rocks below and carried upward. Where this superheated mineral-rich water meets the cold, deep ocean water above, extraordinary things happen. These hydrothermal vent systems are among the most biologically diverse environments on Earth. Tube worms 3 meters long, shrimp with light-sensing organs on their backs, crabs, mussels, fish, entire ecosystems thriving in complete darkness, at pressures that would crush unprotected humans, fueled not by sunlight but by the chemical energy released when reduced compounds from the Earth's interior meet the oxygen-rich water of the deep ocean. Life doesn't just tolerate this environment, it thrives. It builds communities, it reproduces and evolves and fills every available niche with relentless biochemical creativity. And now consider this: if Titan's subsurface ocean is sitting directly on rock, warm rock, heated by the decay of radioactive elements in the interior, just as Earth's interior is heated, then the conditions for water-rock interaction exist. Chemical gradients exist. The potential for something analogous to hydrothermal activity exists, not identical to Earth's deep sea vents, because the chemistry is different, the pressures are different, the temperatures are different. but the fundamental mechanism, liquid water in contact with warm rock, generating chemical energy gradients, is the same. That mechanism is now considered by many astrobiologists to be one of the most universal and reliable pathways to the origin of life, not because Earth proved it once, because the physics and chemistry of it work anywhere the ingredients come together. Water, rock, heat, time. Titan has all four. Now let's talk about time, because this is the piece of the puzzle that rarely gets the attention it deserves, and it changes the calculation about Titan in a profound way. When people think about the search for life on other worlds, they tend to think about it in human timescales. We sent a rover, we'll get data in a few years, we might find something, but life doesn't work on human timescales. Life works on geological timescales measured in hundreds of millions and billions of years. The first life on Earth appeared somewhere between 3.5 and 4 billion years ago, not long after the planet formed. But that life was microscopically simple, single cells, no nucleus, no complex internal machinery. The leap from that first chemistry to something genuinely complex took another 3 billion years. 3 billion years of evolution, of trial and error, of extinction and reinvention, before anything with a brain existed on this planet. If you're looking for life elsewhere, the single most important factor after having the right chemistry is having enough time. Enough time for the chemistry to organize, enough time for the first self-replicating molecules to appear, enough time for evolution to do what evolution does when left alone with a cooperative environment and a patient universe. Mars had liquid water on its surface for a relatively brief window. Estimates vary, but the consensus is that Mars was genuinely wet for perhaps a few 100 million years before its magnetic field collapsed. Its atmosphere was stripped away by solar wind, and its surface water either evaporated into space or froze into the ground. A few 100 million years is not nothing. In the history of Earth, a few 100 million years would take you from the first complex cells to early fish in the ocean. So Mars might have had enough time for simple life to get started, and searching for fossil evidence of that ancient life remains scientifically valuable. But if you're hoping to find something alive on Mars today, you're fighting against the reality that the conditions Mars needed to sustain life have been gone for over 3 billion years. Titan is different. Titan's interior has been warm since the solar system formed. The radioactive decay that heats its rocky core started 4.5 billion years ago and is still ongoing today. The subsurface ocean, insulated beneath kilometers of ice, has likely been liquid for a comparable timescale, not a few 100 million years, billions of years, potentially as long as life has existed on Earth. The clock on Titan did not stop. It has been running quietly, continuously, under that orange haze, while everything that ever lived on Earth lived and died and lived again above us. 4.5 billion years of warm liquid water in contact with rock. 4.5 billion years of organic material raining down from above. 4.5 billion years of chemical gradients, of energy flow, of the patient, indifferent mathematics of molecular interaction. If life needs time, Titan has given it more time than almost anywhere else we know of. And here's where the comparison to Mars becomes not just unfavorable for Mars, but almost absurd in the magnitude of the difference. Not just in terms of atmosphere or pressure or surface chemistry, but in terms of the fundamental question that space exploration is really asking. We do not go to other worlds simply to plant flags. We go to understand where we came from. We go because the question of how life began on Earth, how chemistry became biology, how molecules became minds, is one of the deepest questions the human species has ever asked. And the answer to that question is not locked up on Earth alone. The answer is written across the solar system in worlds that ran the same experiment under different conditions and got different results. Mars can tell us about a world that tried and possibly failed, or succeeded briefly and then lost the conditions needed to persist. That is a valuable story. It tells us about fragility, about how quickly habitability can be lost when the right conditions are not maintained. Titan tells us a completely different story. It tells us about persistence, about chemical complexity sustained across geological time, about a world that has been running its experiment quietly, patiently, without interruption, in a place so cold and so far from the sun that nobody thought to look there for billions, until we sent a spacecraft close enough to actually see it. That shift in perspective, from the warm inner solar system to the cold outer reaches, is one of the biggest intellectual revolutions in the history of planetary science. For most of human history, we assumed that life needed to be close to the sun. The habitable zone, as astronomers call it, was defined as the region around a star where liquid water could exist on the surface of a rocky planet. Earth sits in it, Mars is on the outer edge of it. Everything beyond that was assumed to be frozen, dead, irrelevant, but the habitable zone concept was built on one assumption, that the only energy source capable of sustaining life is sunlight, and life on Earth proved that assumption wrong, not in theory, in practice, in the actual, measured, documented reality of organisms living in the dark, in the deep, powered by the heat of the planet beneath them, completely indifferent to whether the sun is shining or not. The moment we understood that, the habitable zone expanded, not just a little, enormously. Suddenly every moon with a warm interior and a liquid water ocean became a candidate. Europa, Enceladus, Ganymede, and Titan, with its subsurface ocean, its surface chemistry, its nitrogen atmosphere, and its 4.5 billion years of uninterrupted operation, jumped to near the top of every serious astrobiologist's list. But there is something else about Titan that we have not yet discussed, something that goes beyond the question of life and into the question of what a future human civilization might actually look like when it spreads beyond Earth. Because Titan is not just a place to search for life. It is, when you look at it carefully and honestly, one of the most resource-rich and structurally hospitable environments for human settlement in the entire solar system. And when you start doing the math on what it would actually take to build something there, to establish not just a research outpost, but a functioning, long-term human presence, the numbers start to look surprisingly favorable in ways that Mars simply cannot match. We're going to get into all of that now. The energy question, the resource question, the engineering question, and the one comparison that changes every conversation about Mars versus Titan once people actually hear it. The fact that on Titan, the most dangerous thing about living in space is almost completely neutralized by the world itself. You're not going to want to miss this one. Let's talk about the thing that will kill you in space before anything else does. Not the cold, not the vacuum, not the distance, not even the loneliness, though that one deserves its own conversation. The thing most likely to end a human life during long-duration spaceflight and during surface habitation on any world without a strong magnetic field and a thick atmosphere is radiation. High-energy particles streaming out from the sun and even higher energy particles arriving from outside the solar system entirely, called galactic cosmic rays. These particles pass through metal walls, through spacecraft hulls, through human tissue, and they damage DNA. Incrementally, cumulatively, over months and years of exposure, they raise the risk of cancer, degrade cognitive function, damage the cardiovascular system, and compromise the immune response in ways that researchers are still working to fully quantify. This is not a minor engineering inconvenience. It is one of the central unsolved problems of human spaceflight. The astronauts on the International Space Station receive radiation doses roughly equivalent to several chest X-rays every single day. They are partially protected by Earth's magnetic field, which deflects a significant fraction of incoming particles. Astronauts traveling to Mars would lose that protection entirely for the roughly 7-month journey each way, and then arrive at a planet with no global magnetic field and an atmosphere so thin it offers almost no shielding at all. NASA's own estimates suggest that a round trip to Mars, including surface time, would expose astronauts to radiation doses approaching or exceeding the career limits currently set for space workers. And those limits were not set arbitrarily. They were set because the associated cancer risk becomes significant enough to require serious ethical consideration. The radiation problem on Mars is real, it is serious, and it does not have an easy solution. You can build underground habitats, you can use water walls for shielding, you can time surface excursions around solar activity cycles, but you cannot fundamentally change the fact that Mars has no magnetic field and almost no atmosphere, and those two absences mean the surface is continuously bathed in radiation that no long-term human settlement can simply ignore. Now, let's go back to Titan. Titan's atmosphere, that thick 1.45 bar nitrogen blanket we talked about in part 2, is not just good for pressure, it is good for shielding. A column of atmosphere that dense absorbs and scatters incoming radiation. Not all of it, not perfectly, but significantly. The surface radiation environment on Titan, even without a global magnetic field, is estimated to be dramatically lower than on Mars, largely because of the sheer mass of atmosphere above you. You are not standing in the open under a thin veil of gas. You are standing under a sky that is nearly 50% denser than Earth's, made of nitrogen, one of the best common radiation-absorbing materials available, and Titan gets an additional layer of protection from an unexpected source: Saturn's magnetic field. Saturn has one of the most powerful magnetospheres in the solar system, second only to Jupiter's. That magnetosphere extends far enough to partially envelop Titan's orbit, providing an additional deflection of incoming charged particles during the portions of Titan's orbit where it sits inside Saturn's magnetic bubble. It's not complete coverage. Titan does pass outside the magnetosphere at times, but it is a meaningful contribution to the overall radiation environment at Titan's surface that Mars simply does not have any equivalent of. The combined effect of a thick atmosphere and partial magnetic shielding means that living on Titan's surface, from a radiation perspective, is genuinely more survivable for long-duration habitation than living on Mars. The most dangerous, invisible threat in the entire enterprise of human space settlement is substantially mitigated on Titan in ways that require no engineering solution, no special technology, no habitat buried 10 meters underground. The world itself does it for you. That is an extraordinary thing, but radiation is not the only resource question worth asking about Titan. Let's talk about energy, because one of the most common objections raised when people hear about Titan as a destination is the distance from the Sun. Titan orbits Saturn at roughly 9.5 times Earth's distance from the Sun, about 1.5 billion kilometers out. At that distance, sunlight is roughly 100 times fainter than it is on Earth. Solar panels, which are the primary power source for most of our current Mars missions, would be essentially useless on Titan. The math just doesn't work at that distance. So how do you power a settlement on Titan? And this is where the story takes a turn that most people genuinely do not expect. Because the answer is sitting right there on the surface, in quantities that are almost difficult to comprehend: hydrocarbons, methane, ethane, propane, complex organic compounds built from carbon and hydrogen accumulated over billions of years of atmospheric chemistry. We mentioned earlier that the surface organic material on Titan likely exceeds Earth's total fossil fuel reserves by several times over, but let's make that concrete. The methane seas alone, Krakenmar, Ligeamar, Hungamar contain more liquid hydrocarbons than all of Earth's proven oil and gas reserves combined. By a significant margin, this is not a metaphor. This is a volumetric estimate based on Cassini radar measurements of the sea depths and surface areas, combined with density estimates for the methane-ethane mixture. Now, you cannot burn methane on Titan the way you burn it on Earth, because burning requires oxygen, and Titan's atmosphere has essentially none. But you can use methane as a fuel in combination with oxygen that you bring with you or produce on-site through electrolysis of water from the subsurface ocean or from water ice on the surface. And methane-oxygen rocket fuel is not exotic. It is exactly the propellant combination that SpaceX chose for the Raptor engine that powers Starship. The choice was deliberate. Methane is the most accessible hydrocarbon fuel in the outer solar system, and engineers have known for decades that any serious long-range spaceflight architecture would eventually need to be built around in-situ methane production. On Mars, in-situ methane production is theoretically possible but requires importing hydrogen or extracting it from subsurface water ice that is difficult to access, then reacting it with carbon dioxide from the atmosphere through a process called the Sabatier reaction. It works in principle. It requires significant energy input and complex machinery. On Titan, the methane is already there. It is sitting in open lakes on the surface. A pump and a storage tank, combined with an oxygen production system, could in principle provide essentially unlimited fuel for surface vehicles, aircraft, and eventually rockets. The raw material problem, which is one of the most difficult logistical challenges in any space settlement scenario, is solved by Titan's own geology in a way that no other destination in the solar system can match. And then there is nitrogen. Nitrogen is one of the most important elements for any long-term human settlement. It is the primary component of Earth's atmosphere. 78% of every breath you take is nitrogen. It is essential for growing food because plants require nitrogen compounds to synthesize proteins and nucleic acids, and most plants cannot fix atmospheric nitrogen directly. They need it delivered in the form of ammonia or nitrates. It is used in industrial processes, in the manufacture of materials, in the creation of inert atmospheres for sensitive equipment. On Earth, we have an inexhaustible supply of it above our heads. On Mars, nitrogen is present in the atmosphere, but only in trace amounts, less than 3%. Extracting usable quantities would require processing enormous volumes of thin Martian air. Titan's atmosphere is 78% nitrogen, essentially the same fraction as Earth's, at a pressure nearly 1.5 times Earth's. The nitrogen sitting above Titan's surface is a resource of incalculable value for any future civilization trying to build a sustainable presence there. Breathable air composition, agricultural nitrogen, industrial feedstock, all of it available in the atmosphere above you, extractable with technology we already understand and already use on Earth every day. Add to that the water ice available on and near the surface for oxygen production and drinking water. Add the organic surface material for carbon-based chemistry and potentially for construction and manufacturing. Add the energy available from hydrocarbon combustion combined with electrolytic oxygen, and what you end up with, when you lay it all out clearly, is a world that is resource-rich in precisely the ways that matter most for supporting human life and human industry. Not rich in the way that requires decades of technological development to access. Rich in the way that requires the right engineering applied thoughtfully to what is already there. Mars, by contrast, is resource-poor in almost every category that matters. Its atmosphere is thin and mostly carbon dioxide. Its accessible water is locked in ice that requires significant energy to extract and process. Its surface is covered in perchlorates, toxic chemical compounds that contaminate the soil and would have to be removed before any agriculture is possible. Its radiation environment requires shielding solutions that add mass, cost, and complexity to every habitat. Mars is not impossible to settle, but it is genuinely, measurably harder than the popular narrative suggests, and the gap between Mars and Titan in terms of resource accessibility is not small. Now, I want to address something directly because it is the most common pushback I hear when I talk about this topic. And the pushback goes like this: Titan is much farther away, the travel time is much longer, that cancels out all the other advantages. It's a fair point on the surface. The distance is real. Current technology travel times to Titan would be on the order of 7 years using conventional trajectories, though gravity assist maneuvers can reduce that, as Cassini demonstrated by reaching Saturn in 6 years and 9 months using flybys of Venus twice, Earth once, and Jupiter once. But here's what the pushback misses. Distance is a technology problem. Radiation, thin atmosphere, toxic soil, and resource scarcity are physics problems. Technology problems get solved as engineering advances. Physics problems require either accepting the constraints or working around them with enormous continuous energy expenditure. The travel time to Titan will decrease as propulsion technology improves. Nuclear propulsion concepts, already under serious development at NASA and several private organizations, could reduce travel times to the outer solar system to a fraction of what chemical rockets require. The radiation environment on Mars will not improve. The atmospheric pressure on Mars will not increase on any human-relevant timescale. The perchlorates in Martian soil are not going away. When you make a decision about where to invest the enormous resources required to establish a permanent human presence beyond Earth, you are not just making a decision for the next decade. You are making a decision for centuries. And on that timescale, the physics of where you are going matters far more than the current state of your propulsion technology. The closer destination with worse fundamentals is not automatically the better choice. Sometimes the harder journey leads to the better home. There's one more dimension to this that I haven't touched on yet, and it might be the most thought-provoking of all. We've talked about life, about chemistry, about resources, about radiation, but there is a philosophical question sitting underneath all of it, a question about what we are actually trying to accomplish when we leave Earth and what kind of future we are trying to build. That question doesn't have a scientific answer. It has a human one, and in the next part we're going to ask it directly. We're going to talk about the long game, about what a civilization that spreads beyond Earth actually needs to be sustainable across not just decades but millennia. We're going to talk about what Titan offers that no inner solar system destination can provide. And we're going to talk about something that the most forward-thinking space settlement researchers have been quietly discussing for years. The idea that the outer solar system is not the end of human expansion. It is the beginning of something we do not yet have words for. The universe is bigger than Mars, much bigger, and the path to it might run through Titan. Stay with me. If you're still watching, the universe has its hooks in you, and this channel was made exactly for that. Make sure to subscribe and give this video a like. Every week we go somewhere new and come back seeing a little more than we did before. Let's talk about the long game, not the 5-year mission, not the 10-year roadmap. The long game, the multi-generational, civilization-scale question of what it actually means to become a species that lives beyond one planet. Because that question, when you ask it seriously and honestly, changes everything about how you evaluate destinations. It changes what you're optimizing for. It changes what counts as an advantage. And it reveals something about Titan that goes far beyond chemistry and atmospheres and radiation shielding. Something about position, about trajectory, about where in the solar system you want to be standing when the next chapter of human history begins. Start with this. The reason most serious space advocates give for wanting to establish a permanent human presence beyond Earth is not tourism, it is not national prestige, it is not even pure scientific curiosity, though that matters enormously. The deepest reason, the one that animates the most thoughtful people working on these problems, is backup, insurance. The recognition that a civilization confined to a single planet is a civilization one bad day away from extinction, an asteroid impact, a runaway climate feedback, a pandemic more lethal than anything we've faced, a geopolitical catastrophe that goes further than any before it. The specific mechanism doesn't matter as much as the principle. Every egg in one basket is a fundamentally fragile strategy for a species that wants to persist across geological time. If that is the goal, genuine, long-term survival of the human story, then the question becomes not just can we survive somewhere else, but can we thrive somewhere else? Can we build something self-sustaining enough to persist even if contact with Earth were lost? Can we create a second node in the human network that is genuinely independent, not just a resupply depot that collapses without a lifeline from home? And when you ask the question that way, the calculus changes significantly. A Mars settlement, as currently envisioned by most of the major proposals, from NASA's long-term concepts to SpaceX's Starship-based architecture, would be for a very long time deeply dependent on Earth. The reasons are the ones we've been building toward throughout this video. The radiation environment requires continuous habitat maintenance and limits surface time. The thin atmosphere cannot be breathed and provides minimal shielding. The soil is toxic without processing. The nitrogen scarcity limits agriculture. The water is locked in ice that requires energy-intensive extraction. None of these are insurmountable. With enough resupply missions, enough Earth-manufactured equipment, enough energy brought from home, you can keep people alive on Mars. But kept alive with continuous external support is not the same thing as self-sustaining. It is, to use a biological analogy, more like life support than like life. The standard response to this is terraforming. The idea that over centuries or millennia, Mars could be transformed into a world with a thicker atmosphere, liquid water on the surface, and conditions that don't require every human being to live in a sealed container. It's a compelling vision. It has inspired science fiction and real scientific proposals for decades. But honest assessment of the terraforming timelines involved is humbling. The most optimistic serious estimates place a minimally breathable Martian atmosphere thousands of years in the future, requiring a sustained civilization-scale engineering effort that has never been attempted, using technologies that don't yet fully exist, on a planet that keeps losing atmospheric gases to space because it has no magnetic field to hold them in. You would be building a bathtub with no plug, continuously pouring water in and watching it slowly drain away. Titan does not need to be terraformed to be habitable. That is not a small distinction. It is perhaps the most fundamental distinction between the two worlds. The infrastructure required to live on Titan, thermal suits, enclosed habitats, oxygen supply systems, is not orders of magnitude more demanding than what would be required to live on Mars. In some ways it is less demanding because the pressure is already right, because the radiation is already substantially reduced, because the fuel and nitrogen and carbon feedstocks are already there in usable form. The engineering challenges of Titan are real, but they are, in important respects, more tractable than the engineering challenges of Mars once you account for the full stack of what Mars actually requires. And now here's the piece that almost never comes up in the popular conversation, but which changes the long-term picture more than almost anything else. Location: Titan is not just a moon. It is an address in the outer solar system. And the outer solar system is where the resources are. When astronomers and planetary scientists talk about the distribution of material in the solar system, the picture is striking. The inner solar system, Mercury, Venus, Earth, Mars, the asteroid belt, contains a relatively small fraction of the total material available. The outer solar system, Jupiter and its moons, Saturn and its moons, Uranus, Neptune, and the vast reservoir of icy bodies in the Kuiper belt and beyond, contains the overwhelming majority of the solar system's non-solar mass, ice, carbon compounds, nitrogen, ammonia, methane, the raw materials of chemistry, of life, of industry, in quantities that dwarf everything available in the inner solar system. A civilization based on Titan would be positioned at the gateway to that abundance, not trapped in the resource-constrained inner system, fighting over the relatively thin inventory of rocky planets and asteroids, sitting at the edge of a vast, largely untouched reservoir of everything a growing civilization needs. And Saturn itself, the planet Titan orbits, is a resource in its own right. Its atmosphere is predominantly hydrogen and helium, and its gravitational field represents an enormous reservoir of potential energy for spacecraft, using it as a slingshot to go deeper into the outer solar system or back toward the inner planets. Think about how civilizations on Earth expanded. They did not expand by staying close to home. They expanded by pushing outward, by reaching the next coast, the next river, the next continent. Each new position became a base for further exploration, further expansion, further discovery. The history of human civilization is not a history of finding the most comfortable place and staying there. It is a history of curiosity, of movement, of building new homes in places that seemed impossible until they weren't. Titan is not the end of that story. It is a chapter in it. A chapter positioned perfectly, geographically, chemically, physically, to enable the chapters that come after it. A civilization that has mastered the engineering challenges of living on Titan has, almost by definition, mastered the engineering challenges of living anywhere in the outer solar system. The skills transfer, the infrastructure extends, the horizon keeps expanding. Now I want to bring this back to something more immediate, more human, more personal, because all of this talk about civilizations and time scales and resource distributions can start to feel abstract. And the truth is, the most important things about Titan are not abstract at all. They are concrete and specific and, in a certain light, genuinely beautiful. Imagine standing on Titan's surface. You are wearing a suit, not the bulky, pressurized nightmare of a suit you would need on the Moon or on Mars, but something closer to an extremely well-insulated cold-weather suit with a small oxygen supply. The pressure outside is similar to what you'd feel standing at the bottom of a moderately deep swimming pool, present but not crushing. You are not going to explode. You are not going to be flash frozen by contact with the atmosphere. You are standing on solid ground, ground covered with rounded pebbles of water ice, smoothed by the flowing methane rivers that carved the valleys around you over millions of years. Look up. The sky is not black. It is not the thin pinkish grey of Mars. It is a deep, layered amber, a warm orange haze that filters the distant sunlight into something that feels almost like late afternoon on a cloudy autumn day. There is weather here, actual weather, not the thin dust storms of Mars, but a genuine meteorological system. Methane clouds forming and dissipating at altitude, methane rain falling in distant storms, wind moving slowly across the dune fields to the south. You can see weather happening. You can watch a moon of Saturn have a day. Look to the north, and on a clear day, you might catch a glimpse of the sunlight glinting off the distant surface of Ligeia Mare, the methane sea whose shores are only a few hundred kilometers away, if Dragonfly's mapping data leads to where scientists expect it to. A sea of liquid methane, dark and still under that amber sky, stretching to the horizon like an ocean of shadow on a world that knows no rain made of water. And somewhere above you, invisible through the haze, but mathematically present, Saturn hangs. so large that if the haze cleared enough to see it, it would appear roughly 11 times wider in the sky than our moon appears from Earth. Its rings tilted toward you, catching whatever sunlight reaches this far, creating a sight that no human eye has yet witnessed in person, the most spectacular view in the solar system, reserved for whoever is patient enough and brave enough to make the journey. This is not a dead world. This is not a barren, hostile wasteland to be endured. This is an alien world of genuine complexity and strange beauty, one that operates by different rules than Earth, but operates by rules, consistent, physical, understandable rules that science can decode and that engineering can accommodate. It is the kind of world that would, I genuinely believe, inspire awe in anyone who stood on its surface. The kind of world that would remind you, viscerally and immediately, that the universe is not a backdrop for human civilization. It is the context within which human civilization exists, vast and strange and full of places we have not yet imagined visiting. But here's something that brings it back down to Earth, literally. The exploration of Titan is not just about Titan. It never was. Every mission we send to the outer solar system, every question we answer about the chemistry of Titan or the interior of Enceladus or the magnetic field of Ganymede, feeds back into our understanding of our own world, our own origin, our own nature. The tholins in Titan's atmosphere, those complex organic molecules raining down onto the surface, have been proposed as analogues for the chemistry present on early Earth before life began. If Dragonfly's instruments find amino acids in Titan's surface material, it will not just be a discovery about Titan. It will be a discovery about the universality of prebiotic chemistry, about the likelihood that the processes that led to life on Earth are not unique to Earth but are instead a general feature of nitrogen-methane atmospheres irradiated by energetic particles. It will suggest that the chemistry of life is not a miraculous accident that happened once in the right place. It is what chemistry does, given enough time and the right ingredients. And if that is true, if prebiotic chemistry is generic, if the steps toward life are not as rare as we once feared, then the universe is not a mostly empty place with one small exception. It is a mostly full place, teeming with chemistry at various stages of the long journey from molecules to minds, and we are simply one example among what may be an enormous number. That idea, the idea that life might be a property of the universe rather than a miracle of Earth, is one of the most profound shifts in human self-understanding that science could possibly deliver. Titan might be the place that delivers it, and yet, for all of this, there is still a part of the story we have not told. We have not talked about what it would actually take to get there. Not in the vague, we need better rockets sense, but in the specific technical engineering sense of what a Titan mission architecture looks like, what problems it needs to solve, and why some of the smartest people working in aerospace right now believe that those problems are not as far from solvable as the public conversation suggests. We have also not talked about one of the most specific and startling recent discoveries about Titan, something found not in new data, but in old data, reanalyzed with new tools. A discovery about the surface that raises a question nobody expected to be asking about a moon of Saturn, a question that connects Titan to processes we thought were unique to very specific environments on Earth, and that changes what Dragonfly is going to be looking for when it finally lands. Let's talk about getting there, because everything we've covered across this journey, the atmosphere, the chemistry, the subsurface ocean, the radiation shielding, the resources, the long-game positioning, all of it means nothing if the journey itself is impossible, and for most of human history it essentially was. Not because the physics didn't allow it, but because we didn't have the tools. We didn't have the rockets, the power sources, the navigation precision, or the engineering maturity to send anything meaningful to a moon orbiting a planet 1.5 billion kilometers away. And then we did. Cassini launched in October of 1997. It was the size of a school bus, weighed nearly 6,000 kilograms at launch, carried 12 scientific instruments, and was powered by 3 radioisotope thermoelectric generators, devices that convert the heat from the natural decay of plutonium-238 directly into electricity. No solar panels, no sunlight required. Just steady, reliable power generated by the slow, patient decay of radioactive material over decades. Cassini arrived at Saturn in July of 2004, after a journey of nearly 7 years and 6.7 billion kilometers, using gravitational assists from Venus twice, Earth once, and Jupiter once to build up enough speed to reach the outer solar system without requiring a rocket so large it could never have been built. When it arrived, it worked perfectly. For 13 years, it orbited Saturn, making 294 orbits, conducting 127 close flybys of Titan, mapping its surface through radar, sniffing its atmosphere with mass spectrometers, measuring its gravitational field with extraordinary precision. It discovered the subsurface ocean. It identified the methane seas. It measured the tidal deformation that confirmed liquid water below the ice. It found the organic chemistry. It found the missing hydrogen and the depleted acetylene. It transformed Titan from a blurry orange dot into a world we actually know, a world with geography and weather and chemistry, and possibly secrets we have not yet fully decoded. And then, in September of 2017, with its fuel nearly exhausted, Cassini was deliberately guided into Saturn's atmosphere, where it burned up, ensuring that its own microbes, whatever microscopic hitchhikers might have survived the journey from Earth, would never contaminate the moons it had spent 13 years studying. A final act of scientific integrity, a spacecraft choosing its own grave to protect the worlds it loved. We know how to do this. We have done it. The journey to Titan is not theoretical. It has been made. The question is not whether we can get there. The question is what we send next and what we are trying to find. Dragonfly is the answer to that question, and it deserves more attention than it gets in the mainstream conversation about space exploration. Let me paint you a picture of what this mission actually is, because the engineering of it is as remarkable as the science it will do. Dragonfly is a dual quadcopter, 8 rotors arranged in 4 pairs, giving it redundancy and stability in Titan's thick atmosphere. It weighs roughly 450 kilograms. It is powered by a multi-mission radioisotope thermoelectric generator, the same basic power technology that ran Cassini and currently powers the Curiosity and Perseverance rovers on Mars. It carries a mass spectrometer for chemical analysis, a gamma-ray spectrometer for measuring surface composition from above, a suite of meteorological sensors, cameras, and seismic instruments. It is, in every meaningful sense, a flying chemistry laboratory. The plan is this. Dragonfly lands first in the Shangri-La dune fields near Titan's equator, a region of relatively smooth terrain that is well mapped from Cassini data and rich in organic material. It collects samples, runs its instruments, charges its batteries from its nuclear power source during Titan's roughly 16-day cycle of light and dark, and then, and this is the part that still feels almost surreal when you say it out loud, it flies to the next site, lifts off the surface of a moon of Saturn, rises into that thick amber atmosphere, and flies, under its own power, on another world, several kilometers at a time, eventually covering more than 175 kilometers across Titan's surface over the planned mission duration, visiting dune fields, river channels, the edges of impact craters, and eventually a target called Selk Crater, an impact site where the heat of the impacting meteorite melted the water ice beneath the surface and mixed it with the organic material above. creating a temporary liquid water environment that persisted for potentially hundreds to thousands of years before refreezing. Selk crater is the scientific heart of the mission, because in those brief windows when liquid water and organic material mixed, when the hot, chaotic aftermath of an impact turned a frozen surface into a warm chemical soup, prebiotic chemistry could have occurred. Amino acids could have formed, more complex structures could have assembled, and then the water refroze, locking whatever formed inside, preserving it in the cold like a biological time capsule. Dragonfly is going to fly to Selk, land inside it, drill into its floor, and read whatever chemistry is written there. If it finds amino acids, the scientific community will erupt. If it finds something more complex, nucleobases, lipids, structures that look like the precursors to cell membranes, the conversation about life in the universe will never be the same again. And if it finds something entirely unexpected, something that doesn't fit any of our current frameworks, that will be most exciting of all, because the universe has a long history of not fitting our frameworks. Now, the discovery I promised you, the one hiding in old data found with new tools, raising a question nobody expected. In 2023, a team of researchers reanalyzed Cassini's near-infrared spectroscopy data from Titan's surface using machine learning algorithms that were not available when the original data was collected. Their goal was to map the distribution of different surface materials more precisely than previous analyses had managed. What they found, in a specific region near the boundary between a dark organic dune field and a brighter icy terrain, was a spectral signature they did not expect. A chemical fingerprint that matched a class of compounds called acrylonitrile, also known as vinyl cyanide. Vinyl cyanide had already been detected in Titan's atmosphere in 2017 using the ALMA radio telescope array in Chile. That detection made headlines because theoretical work published the same year suggested that vinyl cyanide molecules, under the conditions present in Titan's methane seas, could spontaneously assemble into membrane-like structures, not cell membranes made of phospholipids the way ours are, but functional analogues, flexible, stable, self-assembling sheets that could in principle form the boundary of a cell-like compartment in liquid methane. The theoretical paper calculated that a single cubic centimeter of Titan's methane seas might contain enough vinyl cyanide to form 10 million such membrane structures, 10 million per cubic centimeter. In a sea that covers an area the size of the Caspian Sea, the atmospheric detection was remarkable enough, but the 2023 reanalysis found it concentrated on the surface, near the interface between organic dunes and icy terrain, precisely the kind of boundary zone where chemical gradients are steepest, where different materials meet and react, where the interesting chemistry tends to happen, not distributed uniformly, concentrated, localized, as if something, some process, some physical or chemical mechanism, possibly something biological, was organizing it. Nobody is claiming this is proof of life. I want to be absolutely clear about that, because clarity matters here more than excitement. The acrylonitrile concentration could have a purely physical explanation related to how organic molecules sort themselves along terrain boundaries under Titan's specific atmospheric and thermal conditions. That explanation needs to be thoroughly investigated before anyone draws stronger conclusions. Science is careful precisely because the stakes of being wrong are so high. A false positive in astrobiology does enormous damage to the credibility of the entire field, but here is what is true. The molecules capable of forming cell-like membranes in liquid methane are present on Titan's surface. They are concentrated in locations that are chemically interesting. They are there in quantities that are, by any reasonable measure, extraordinary, and we have a spacecraft being built right now that will fly to Titan, land on its surface, and directly measure what is happening in environments exactly like the ones where these concentrations were found. The question is on the table. Dragonfly is going to answer it. Let's come back to Earth one more time. Let's come back to you. You are made of atoms that were forged in the cores of stars that lived and died before our sun existed. The carbon in your body, the oxygen in your lungs, the iron in your blood, none of it was made here. All of it was made out there, in the nuclear furnaces of stellar interiors, scattered across space in supernova explosions, gathered by gravity into a new solar system, cycled through oceans and atmospheres and living things across 4.5 billion years of Earth history, and eventually assembled into the specific, unrepeatable arrangement of chemistry and electricity that is you right now, watching this video and wondering about a moon of Saturn. You are the universe looking at itself. You are the thing that star stuff does when it gets complicated enough. It wonders where it came from. It asks questions. It builds telescopes and spacecraft and mathematical frameworks to reach across the void and understand what is out there. That impulse, that deep, restless, irreducible need to know, is not separate from nature. It is nature. It is the universe's own curiosity, expressed through the only instrument it has so far developed that is capable of curiosity, you. And Titan is one of the places the universe has been quietly running its own experiments unobserved for billions of years, assembling complex molecules in an orange haze, cycling methane through rivers and seas and clouds in an echo of Earth's water cycle, possibly, crossing the threshold from chemistry into something that moves and reacts and persists and, in whatever sense the word applies to a cold methane sea on a moon of Saturn, lives. We do not know yet. We genuinely, honestly, scientifically do not know. And that not knowing is not a failure. It is an invitation. It is the universe leaving a door open, waiting to see whether we are curious enough, brave enough, and wise enough to walk through it. Mars is close. Mars is familiar in the way that rocky, reddish, cold deserts are familiar. A world that looks like something from our own experience, scaled up to planetary size. It captures the imagination because it feels almost reachable, almost manageable, almost like a version of something we already know, and there is value in that. There is real science to do on Mars. There are real reasons to go. But Titan is something else entirely. Titan is genuinely alien, a world operating on different chemistry, under different rules, at different temperatures, telling a different story. And the most important discoveries in the history of science have almost always come not from studying more of what we already understand, but from encountering something genuinely different and having the intellectual courage to follow it wherever it leads. The history of astronomy is a history of expanding circles. Earth at the center, then the sun, then the galaxy, then billions of galaxies, the habitable zone around the sun, then around other stars, then in the subsurface oceans of icy moons, far from any star's warmth. Every time we drew a circle around what was possible, the universe drew a bigger one. Every time we decided we understood the boundaries, reality exceeded them. Titan is outside the circle we thought we understood, and that is precisely why we need to go. So here is the summary of everything we have covered, the full picture assembled from all its pieces. Titan has the only atmosphere in the solar system, besides Earth's, thick enough to walk outside in without a pressure suit. Its surface pressure is higher than Earth's. Its nitrogen-rich atmosphere shields against radiation better than the near vacuum of Mars. Its methane cycle mirrors Earth's water cycle in complexity and scale. Its surface is covered in organic material several times more abundant than all of Earth's fossil fuel reserves. Its subsurface ocean, confirmed by tidal measurements, likely sits in contact with a rocky seafloor, creating the same kind of water-rock heat interface that hosts the most biologically productive environments on Earth. It has had 4.5 billion years for its chemistry to develop, Uninterrupted, continuous, patient. It holds the molecules theoretically capable of forming cell membranes in liquid methane. It shows chemical anomalies at its surface that match the predicted metabolic fingerprint of life. It offers energy, nitrogen, carbon, and raw materials in forms that are accessible without technologies we do not yet possess. It is positioned at the gateway to the resource-rich outer solar system. And it is the destination of Dragonfly, one of the most scientifically ambitious and technically extraordinary missions in the history of planetary exploration, launching in 2028 and arriving to begin answering the deepest questions we know how to ask. Mars is not a bad destination, but Titan is a better one, not marginally, profoundly, in ways that become undeniable the moment you look at the full picture rather than just the distance. The real reason we should visit Titan instead of Mars is not any single fact. It is the accumulation of all the facts together, the way they layer on top of each other and reinforce each other and point, collectively, toward a world that is trying to tell us something about chemistry, something about life, something about the universe's willingness to experiment in the cold and the dark, far from the warmth of the sun, in places we almost didn't think to look. We almost missed it. We almost looked away. We almost stayed focused on the familiar, the close, the comfortable. Thank goodness for the people who looked further. If this video made you see the solar system differently, if it made Titan feel real and complex and worth caring about, then please share it with someone who loves space, who loves science, who loves asking big questions. Hit the like button if you made it all the way here, because it genuinely helps this channel reach more people who are hungry for exactly this kind of deep, honest, science-grounded exploration. Subscribe if you want more, because there is so much more universe to cover, and we are just getting started. And I'll leave you with one final thought. The next time you look up at a clear night sky and find Saturn, that steady yellowish point of light that doesn't twinkle the way stars do, know that orbiting it, invisible to your eye but absolutely real, is a world bigger than Mercury, wrapped in orange haze, covered in organic seas, hiding a liquid ocean beneath its frozen skin, buzzing with 4.5 billion years of chemistry we don't yet fully understand. It is out there right now. It has been out there your entire life, and your parents' lives, and every human life that has ever been lived on this planet. Waiting, patient, full of questions that only a species curious enough to build spacecraft and send them across 1.5 billion kilometers of space will ever get to answer. We are that species. This is our moment. And the universe, I think, is watching to see what we do with it. Thank you for watching.